All right, welcome to Chapter 9, Section 3, called Similar Triangles. This is for Integrated Math 2, or IM2. So first couple of things, just to go over the front screen here, you'll see a due date on your student screen. You don't see it on my teacher preview, but you'll see it on your student screen. The second thing you'll see is the number of attempts. You always have unlimited attempts on homework, tests, and quizzes. Number of questions just tells you how many are on this particular assignment. Grading policy is best score, which is always active. So whichever one is the best score is one you get to keep, which refers to the attempts. Partial credit is always enabled, so if you answer 1 of 4 questions correctly, you get credit for the one question, or however many you answered correctly. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. And what that means is once I click start, on the bottom right hand corner here, there will be a submit assignment button. You need to make sure that you click that submit assignment button when you want to finish. That's how we finish our assignments. So when we want to leave this screen, whether or not we finished all 4 questions, we click the submit assignment button. It does 2 big things. The first thing it does, which is what that first screen told us, is allows us to work on other assignments. If we just close this tab or we close our computers, it locks out every other assignment and our resources. Because Alex assumes we want to leave this attempt open, and it's trying to do that for us. So it literally locks everything. It saves your place when you click submit assignment. So if you've answered some of these questions already, it's going to know that. So don't worry about that. So go ahead and click that button so it doesn't block out the whole system. And the second thing it does is it affects the grade book when you click submit assignment. So your teacher can actually see what you've been working on. Up until the point you click submit assignment, your account's kind of frozen in that assignment. We can't see anything you've been doing. So 2 very big reasons, always click submit assignment. On the right hand side here, we always have explanation, example, and message center. Sometimes the calculator is there, so it's there for this one. Explanation tells us we're going to lose our current question attempt because it's going to give us the answer to this question. So it's not going to give us the answer and then let us come type it in. That's not how this works. Explanation does in fact give us an explanation very similar to what it is we're looking at. So this one's a little different, but it's still 2 triangles. The one we're looking at here is just 2 triangles kind of inside of each other. These are 2 triangles next to each other that are sharing one vertice. But we can see, we can set up a proportion based on the 2 triangles and then solve our proportion. You can click on this for another example, and then you can also message your teacher directly from the screen so that we know where to come help you. All right, so let's go ahead and get started on this problem. So in the example, what it was showing there was, why don't I see my color wheel? Interesting. All right, usually a little color wheel pops up here, but it's hidden from me. So in the example, what they show, and I'm just going to draw this over here, and when you draw this diagram, it doesn't need to be perfect, something like that, and I can see that there's these 2 little squares. What that means is these are right angles, right, and this guy is a right angle. So I have 2 right angles here, and we're under the assumption that these are similar. We can actually go through and prove this using angle-angle similarity. We didn't really go through this property as far as actually teaching it in the class. They just kind of started throwing it at us. So angle-angle similarity means if I have 2 angles of one triangle that are congruent to 2 angles of another triangle, the triangles are similar. Not necessarily congruent, but they're similar. They could be congruent, but we'll just call them similar because we don't necessarily know. And in this case, we can kind of see this guy is much smaller than this one, so they're not congruent. Congruent means same size and shape. So similar means they're the same shape, not necessarily the same size. So the reason we can use angle-angle is because if I go, anytime I have like an X with 2 lines, which I can see in the middle here, I can go across the vertex, and this is called vertical angle. So this is a vertical angle, and anytime I can do that, a vertical angle is congruent. So I have angle-angle on the bottom triangle here and angle-angle on the top triangle. So they are similar triangles. All right, I'm going to take some of this stuff away here just so it gets out of our way, because I think that's too much junk in the way. So let's go ahead and put the measurements they have here. So they give us 5 for this one, 3, 7.5, and x. And they want us to find x. So what they do, if you look at the example, I guess I'll put it in pink. They go around and they label the triangle. So they go like A, B, C, D, E, something like that. So they give all the vertices a name, so then they can go AB corresponds to DE, and DC corresponds to BC. So this just gives us a way of naming it. The other way that I tend to do it is I look at kind of the direction of what I'm doing. So if I'm looking at this one, I have this far point or far vertice, and it's going to the right angle, like that. So I can describe the other one the same way. So I go to the other triangle, I have this far vertice, so this one that's kind of out away from everything. And if I go to the right angle, these two are corresponding sides. I kind of like to describe it that way. It makes a little bit more sense generally when I'm starting to teach this to students, when you can kind of use these descriptions. So you have this far off vertice going to the right angle, far off vertice going to the right angle. It just kind of gives this direction, this visual direction. So these guys are corresponding. And then I also have this middle point to the right angle, or I could go right angle to the middle point here. Either way, it's not a big deal, but middle point to the right angle. So these two are corresponding because they're doing the same thing. It's going from the middle to the right angle, middle to the right angle. Or if I read it the other way, right angle to the middle, right angle to the middle. Either way, as long as I just can describe it the same way. So again, you can use it their way where you're naming all the vertices and showing, you know, which sides correspond to each other, but you can also use this kind of visual direction. It's just up to what makes a little bit more sense to you. I think I'm going to make this a little bit bigger. The pen's a little small. It's just writing teeny tiny to me. All right, so we're going to write a proportion using these so that we can compare. And we've done this. We were doing this in chapter 6, so this shouldn't be brand new to us. Hopefully we've gone through all those sections and we understand that we can compare corresponding sides to each other when we have similar triangles. And the reason is, whatever I increased 7 or 5 by to get to 7.5, so it's not a whole number necessarily, it's part of a number, but I increased 5 to get to 7.5. Whatever I increased it by, whatever I multiplied by, I would have had to do the same thing to x to get to 3, because they're corresponding sides. So that's why we can compare them. The sides should have been increased or decreased, and by increased I mean multiplied, by decreased I mean divided. So they should have been multiplied or divided by the same number, same ratio, or scale factor to get from one to the other. Okay? All right. So we're going to go ahead and we're going to look at the small triangle. You could also say the top triangle, however you want to do that, and large triangle. This is just going to help me remember I want the numbers for the small triangle on the top. I want the numbers for the large triangle on the bottom. Okay? So the small triangle, I'm going to say that 5 compares or corresponds to 7.5. So these two have two numbers in it, which we need at least one of our fractions to have both top and bottom, numerator and denominator, filled in, because that's going to be basically our scale. And then for the other fraction, for the other part of the proportion, we're going to look at the variable that we're searching for. So in the small triangle, we're looking for x, and that corresponds to 3. So now we have our proportion written, and we can go through and we can cross multiply. So I can go cross from top to bottom. 5 times 3 gives me 15, and that's going to equal, I guess I'll do this other guy in red, if I go across the other way, 7.5 times x, which is just 7.5x, like that. Because we just kind of squish them together, right? So now we have this piece. I have to get x by itself, so I need to take that 7.5 and divide on both sides. And I believe we're going to get 2 here. So we'll go ahead and put this in the calculator just to make sure I'm not losing my mind. Yay! 15 divided by 7.5 is 2. So x is 2. And that compares. That's the same ratio, 2 to 3 is the same ratio that 5 and 7.5 are. So they're kind of the same difference or same multiplier there. I know that sounds funny, but all right. So we'll go ahead and do 2. 2 is not the multiplier. I don't want you to think that. 2 is actually the length of x. So if we wanted to know what the multiplier was, we would have to reduce either 2 over 3, which actually is reduced. That would be the scale factor, 2/3, which we could reduce 5 and 7.5 the same way by taking 5 and 7.5 and taking the decimals out. So if I move, dang it, if I move this decimal over, I'd have 75. I have to move this over once because I moved that over once. So I'd have 50 over 75. Well, if you kind of think about these, they can both be divided by 25. This can be divided 2 times. This can be divided 3 times. So I can do that same thing with this. That's not the only way, of course, to do that. I could have also looked at, how many 0.5s are in 5, how many 0.5s are in 7.5. That would have gotten rid of the decimal and then reduced that. A couple different ways to reduce decimals when we have fractions. But really the scale is 2/3. So 3 is 2/3 of, 2 is 2/3 of 3. I was saying that backwards. Because 2/3 is smaller, right? All right, let's go ahead and check that. Yay! Okay. We will, no. All right. So now, indirect measurement is a way of measuring things that would be very difficult to measure kind of actually with a measuring tool. But we can find the measurement of things using other things around them, especially if we have similar triangles. So let's read this problem. A pole that is 3 meters tall casts a shadow that is 1.34 meters long. At the same time, a nearby tower casts a shadow that is 38.25 meters long. And how tall is the tower? Round your answer to the nearest meter. All right, let's draw a picture because it's way easier to picture this, actually looking at it. So we have kind of a pole, and I'll put like a little circle on top, like a weird little flagpole, I guess. I don't know. And this guy is 3 meters tall. And it casts a shadow. So here's my very awesome shadow for my flagpole or whatever pole this is. And it's 1.34 meters. Oh, should it have been that long? Probably not. Let's shorten that up just a little bit just to, what's going on? I'm going the wrong way. So I'll make it very short like this. 1.34 meters. I should have looked at that before I started drawing shadow. I read it and it didn't stick in my brain when I started drawing. So here's the pole, here's its shadow, right? And then it says nearby there's a tower, and the tower casts a shadow that is, and I'm going to make this a little bit bigger. It's tower seems, that's going to be a little bit wider, right? And we're just going to call that good enough. It's 38.25 meters. I know that's not comparable. We don't have to draw them to scale. We're just kind of drawing a picture to help us match it. But here's my tower. So there's my tower. Kind of a weird tower, I know, but there it is. I'm not really sure what it's supposed to look like. It's just a tall building. We don't know how tall this tower is. It says, how tall is the tower? So I'm just going to say T for tall. I don't know. And it wants us to round our answer to the nearest meter. So we're going to round it off when we get it. Well, how do we know that these are comparable triangles? I don't see a triangle yet. So when we're looking at the triangle, and I'm doing this in yellow on purpose, we have the sun shining down here like this. So the sun is shining down, and that's what's casting the shadow. This is blocking the sunlight, so it's causing a shadow here. So same thing, if I were to scroll down here, and let's see, I'm going to try to do this nicely. Nope. I'll do it from here, like this. So, and I didn't draw these perfect. These two should be parallel lines. They look not too horrible, honestly, as far as parallel line goes. I don't think they're perfect. They definitely would clash into each other at some point here, but close enough. So, and again, the reason I'm using yellow is it's kind of like the rays of sun coming down, because we have the sun, very far away, casting this light down, and whatever's in the way of the light is creating the shadow. So this angle that's created is going to be the same by the sun because it's in the same position in the sky from the flagpole to the tower. Okay, and they say nearby because that does matter, based on how you're on Earth and stuff, where the angle of the sun would be. So as long as we're nearby, it's the angle's not going to change. The other angle that would also be the same would be this guy that's down here, the angle created at the ground of the rays of the sun. That would also be the same, for the same reason as the top one is the same. The sun is in the same position in the sky, shining down at the same angle. So this angle of elevation here would be the same as the angle of, this is called the angle of depression, which I know students always get a little giggle out of that one. The pole and the tower we're going to assume are at a right angle to the ground. So they're perpendicular to the ground. So we can actually show that all three angles of the little triangle created by the flagpole are congruent to all three angles of the large triangle created by the tower. That doesn't mean they're congruent, just means that they're similar. All we need are two of the angles. We just need angle. So that's why I went through and just showed you why this works. It's based on the sunlight coming down at the same angle. Okay? So we're going to do the same exact thing we did on the last one. This one I think is a little bit easier to compare because we have the height of the object or the shadow of the object. Okay? So we have the pole and we have the tower like this. And then I can say the, let's see, we'll go with height on this side. Why not? Height. And we'll go with shadow. So I can actually give myself a little map of how to fill this in. So the height of the pole goes on top here. That's 3 meters. The height of the tower, that goes on the bottom. Well, I don't know that. That's T. The shadow of the pole, that goes on the top on this side. So, and then the shadow of the tower, that goes on the bottom. 3, 8, 25, like that. So it gives me like this little map. We just want to make sure it's comparable. So the heights would be comparable to each other. The shadows would be comparable to each other. So this one's, kind of like directional on that other one, but we're comparing the actual kind of object, I guess, if we think of the shadow as an object. All right, so we're going to go through and we're going to do our cross multiplication here. So we're going to have 3 times 38.25, and I'm not going to do that one in my head because I don't want to try to mess that one up, times 3, so 114.75. I don't know why there's 2 1s there. Go away. 14.75, there we go. Equals, for whatever reason, I'm very worried about this color coding. All right, and then we have T times 1.34. So this is the idea, cross multiplication. And again, we practiced that quite a bit in chapter 6. So we're just continuing this idea. When we have a fraction equaling a fraction, we can use cross multiplication to get rid of the fractions so that we can solve the equation. So we have 1.34 T, because we just smush them together and it's proper to have the coefficient first instead of T 1.34. Really means the same thing. It's just it's proper to have it in front. That's what Alex will be expecting if it asks you to type it in this way. But it wants us to go to the next step. It wants us to actually solve for T. So I need to divide both sides by 1.34. I don't know why I said 3.14. I'm just going with pi on that one for some reason. Divided by, is it working? Divided by, there we go, 1.34. And we get 85.63, and that would be meters equals T, because anything divided by itself cancels out. So 1.34 divided by 1.34, even though they're decimals and, a little bit more complicated looking, it's still a number divided by itself, so it cancels out. All right, so it did say to the nearest meter. So 85 is the meters, and so we want to look at this one. I'm going to drop these guys off for a minute. I do need to look at this one before I completely delete it. This is going to help me know if I'm rounding. So 6 is 5 or bigger, so that means that I'm going to round this meter up to the next one. If it was 4 or smaller, the decimal simply just drops off. That's what rounding down means. Rounding down doesn't mean we actually change the number. It just means we round the decimals off. Rounding up means I'm going up to the next whole number. All right. Perfect. So for this one, we're going to be identifying and naming similar triangles. So we're going to decide whether the triangles are similar. If they are, write a similarity statement and state the reason justifying their similarity. So with this one, we've gone through quite a few congruencies for triangles. Now we're starting similarities. So if you notice, they're named exactly the same. Angle, angle, side, 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 angle, side. But this time, instead of congruent, you see similarity. So remember, similar means that they're the same shape, but they're just different sizes. So one's larger, one's smaller. So we need to make sure that they are in fact similar triangles before we do this. So we just have to compare the two triangles. And we have to either have two angles that are congruent, side, side, side. So that doesn't mean that they're congruent anymore. It means that they are similar or proportional to each other when we're talking about the sides. The angles will actually be congruent to each other. And I can show you, I can draw a triangle here like this. Boom, boom. So here's a triangle. And if let me see, I can lasso this guy. Oh, I didn't do a very good job on that one. Let me try again. I still didn't do a very good job. Darn it. So I'm going to copy paste. So cut off just a little bit there, but I can move this around so we can kind of see if it's there, except for the little spaces that I cut off there, but it fits very perfectly. If I make this smaller, like this, so I'm dilating this triangle. So I've made it smaller. But what I haven't changed is the angles. So that angle fits, this bottom left angle fits, and the right angle at the bottom fits. They all fit. Same thing is true if I make it larger, like this. So I can dial it up. So, but I haven't changed the angles. The side lengths should hopefully be able to see that's much larger, right? Because it was this length, now it's this much longer. So I like that diagram because it's very easy for us to see that, changing the size doesn't change the angles, but it does change the side lengths. So with this one, what we want to do is make sure that they match up. So we're looking at ABC. So A, B, C like this. So it looks like that would go E, D, F if we can match it up. So AB is 6. And if I'm looking at this correctly, for AB to ED, that would be over 3. So that would mean this would reduce down to 2. Or I multiply by 2 to get from 3 to 6. Now if I look at this one and I go 4 to 5, well, that's not true. 4 times 2 is not 5. That would be 8, right? So this proportion would not work. And the top one, going from 9 to 6, would also not work. That would reduce down to 3 and 2, but not the same thing. So they're all different, all these proportion sides. And I don't see any way for me to make them all the same. Yeah, there's no way. And I wouldn't trust it. They slightly look similar, but even if I switched it around and said 4 and 6, so 6 to 4 like this, and I went 3 over 2, and then I went 5 over 3. So I kind of flipped this around, like it was transposed. That would stay 5 over 3. So those still don't match. So there's not really any way for me to say that these are similar. So I'm going to say not similar. On this one, since I'm given angles, I need to prove that at least 2 angles are congruent. Well, I have 90 and 90. So I'm part of the way there. What I need to do is I need to know what either this angle is or this angle is. If I calculate this and this is 35, well, I have it matching. If I calculate this one as 55, then I have these two matching. I don't have to do both. So 90 minus 55, and the reason I'm subtracting from 90 is that's all that's left for these two. So if I have a right triangle, the two acute angles have to add up to 90 degrees. So I'm just kind of cutting out this 90 here from the 180 to make that a little faster. And then I get 3, so 35. So that is 35 right there. So that would mean that that is 55. So angle-angle similarity tells me that these two triangles are in fact similar. So I need to make sure I match them up. J, K, L. So it goes from the 55 to the 90. So 55 to the 90. So I'm going to go H, I, G. G. And then this bottom one. The only thing I have on this bottom one would be these vertical angles. I have no other markings at all. So there's no way for me to prove another angle congruent because I don't know if anything's parallel. They don't look parallel. I don't know if any side lengths are similar to each other because I don't have any. So I'm going to say not necessarily. I don't know. There's not enough information on that one. All right, so then we're going to move to a proof. And one thing that's a little different with the proofs that I do in class versus the proofs we do in the video is in the video you can see I don't know how many steps there are. I just have to work through this. In class, we have it on a worksheet and you can see how many steps I'm expecting. So it's a little different when you're doing it on your own here. So we're going to use the given information for triangle A, B, C, and E, D, C. So they gave us the order here. What we want to do is we're given that A and E are congruent. I'm going to send this to proof. If I click send to proof, it sends it here and says given. If I type this in, I have to choose given from my list and validate. So it's just, two ways to do the same thing. Just send to proof is a little faster. So I know already, I'm going to draw this guy really quick because this is a little easier. So we want to prove that they're similar. That's what this little wavy piece means. It means similar, not the same, not congruent, similar. So E, C, D, A, B, and we know that A is congruent to E. They told us that already. So now I need to look at this triangle. The only possible thing that I could prove on this triangle would be vertical angles. There's no other given information. I don't know about any lines being parallel, which they may be parallel, but I don't necessarily know that. I do believe they are parallel in the end because they are similar triangles. I know I can prove it using this vertical angles, but this is the only thing that I can use. I need to make sure that I label this correctly. So it's angle ECD, and that's going to be, not equal to, darn it, congruent to angle, and I'm going to go ACB. ACB, and I'm going in corresponding order for those because it goes E, which I know corresponds to A, and then down or over to C and down to D. So I'm kind of going in this way, and then I started with A because it corresponds. So E and A correspond, C and C correspond, D and B correspond. I can't just say angle C is congruent to angle C because angle C could be either one that we're talking about here or it could be these outside ones. So we have to use those three angles to show that. And this is vertical angles, so I just need to scroll through the list and find out vertical angles property. I'm going to validate. All right, so now I've proved that two angles of this left triangle are congruent to two angles of this right triangle. So the two triangles are similar by angle-angle property. So this was a pretty short one here. And make sure we don't want congruence. We want to go down here and find similarity. They're not congruent, they're similar. All right, and now I see that check, so I can check this and be done. So don't click that check until you see this screen, otherwise you'll get it marked wrong. All right, well that was section 3, and I will see you in section 4.